Okay, good morning, good afternoon, everyone. My name is Gururaj Shimpi, and I'm a fourth year BTech student at NITK in the Department of Electronics and Communication Engineering. This is my seminar for image processing and computer vision. So I'm going to talk about the topics of compression techniques and with more detailed focus on PDF compression. So we're going to begin with traditional compression methods such as JPEG and PNG. Then further, we are going to talk about PDF compression and finally look at state-of-the-art or AI-based compression methods that are being worked on right now. So without further ado, let's start. So uh, why image compression, right? So image compression reduces your data size significantly while preserving visual quality. Like you can see on the image on the right side, the dog picture originally took up 824 KB in JPEG, which is already a compressed form of an image. And after applying 50% lossy compression, it amounts to only 76 KB, which is a very significant reduction in the data consumption, about 10 times lesser. And at the same time, the image looks almost the same. So here, image compression algorithms help us store and save massive amounts of data, which is very significant because nowadays, with the onset of digitalization, you have cloud storages which have huge terabytes of data, and this helps conserve so much of that data, right? So why do we need compression? So as you can see, the use of software and software related products and cloud related products has been increasing quite vastly recently. And so in 2010, you had about 2 zettabytes of data, and now you have almost 100 times the amount. That is 181 zettabytes. And soon in 2026, I'm predicting there'll be much more need of data. So first thing, the amount of data to be stored is increasing a lot. And secondly, compression helps us retrieve and store data very quickly. So it helps in transferring files much quicker and so helps in increasing the bandwidth or saving the bandwidth, right? And it reduces server costs. So types of compression. So you have three types of compression mainly. One is lossless compression, where basically you store the image as all you use some sort of mathematical manipulations and store the data in the image in a shorter form or use lesser bits than that are required. But in essence, you don't at all lose any data. So suppose I have some series of bits. I choose to encode it in such a way by exploiting patterns in the data to make sure that the amount of bits needed are lesser, right? So you can use many techniques such as Hoffman coding, etc., for lossless compression. We'll come to these later also down in the seminar. And one, you have lossy compression. So lossy compression allows for partial loss in data, and it's very good for especially photos. So for example, on the image on the right again, we have JPEG images. So you have 938 kilobytes originally, and now after lossless compression, it's about 792 kilobytes. And after lossy compression, it is only 84 kilobytes. Meanwhile, all the three images look more about the same to the human eye. There are some differences here and there, but as to a person viewing the image, there is not much of a difference. And anytime, obviously, you do compression, so there's going to be a trade-off between the size and quality. So you don't want to downsize it so much that the data itself becomes redundant. Right? So yes, coming to basic compression techniques. So in class, we have already discussed Hoffman coding. So what Hoffman coding very briefly does is whichever data is more frequently used in the image, we choose to give it lesser number of bits. If it's the most repeated, it will be represented by only one bit. and then so on, you keep arranging the other data codes that come in. So this essentially helps reduce the number of bits that are required to store the data. Right. So next you have RLE compression. So RLE compression stands uh, RLE compression. So what you do is, suppose you have the pixel size, let's say pixel intensity of 121 repeated 10 times throughout the image, right? Like it could be just that there's a background and you have similar intensity values coming all over it. So in that case, what we do is we store the 121 10 times instead of storing it as uh, 121, which would require, let's say, about 8 bits, and 10 times like that, so 80 bits. Instead of that, what you just store it as is 10 as an array where you have 10 comma 121. So basically, this just means that 121 has been repeated 10 times, right? So this helps us save a lot of bits in this way. And then there's another technique called LZW. So LZW exploits a dictionary-based encoding. So anytime it encounters a new intensity value, it stores it in a dictionary and assigns it one particular bit value and continues to keep doing so, right? Now we have a small compression flow here where this is kind of like JPEG. It's actually JPEG compression. So where you start with the image, divide the image into sub-blocks, 8 to 8 blocks, perform DCT on each sub-image, quantize it, then format it in a from 128 to 127, and then place them in zigzag order. So it's easier to even decode the image using the zigzag manner. Right. Now let's go to transform-based compression. Right. So like we discussed above, we use DCT. So DCT was originally used in JPEG images. So what a DCT is equivalent in mathematical terms is that you're taking basically like your Fourier transform, but you're ignoring the imaginary components. So essentially you do the same thing, but don't apply the one where you multiply it with sine wave, where you multiply by sine 2 pi f naught t. Instead, just multiply your sequence and weighted multiply and add your sequence of only with cos. So you have only real components in the picture. So this is what was originally used. So on the right, like we spoke before about a compression technique, here the sub image has been divided into 8 cross 8 blocks, and you have applied the DCT on each sub block. So here you can see there is UM, XIJ, UNT. This is nothing but UM and UN are the matrices for DCT compression. It's a DCT transform. So you'll have the matrix values already calculated. You can just multiply them to get this transform. Now, looking a bit deeper into the transform itself, you can see that it's been divided into various colors, right? There is a blue color, yellow color, slightly greenish color. So basically, these color changes signify frequency changes in the particular subimage. So the more color changes are there, a higher frequency components or more frequency changes there in that, right? But there is a drawback of DCT, and DCT's drawback is that it edges are not detect. Okay, there was a small issue, and now we're back. So yeah, continuing to where I left off, DCT has a small issue while detecting edges. They look a bit blurry and are not quantized properly. So there's another type of transform that is used that is called DWT. That is your discrete wavelet transform. So discrete wavelet transform basically takes wavelets and samples the wavelets and then applies your transformation matrices on it. So it's better at preserving edges and it's used currently in the JPEG 2000 format. So these transient-based compressions remove important details such as higher frequencies, and you lose that data. So yes, so coming to comparing JPEG versus PNG, right? So like we discussed before, JPEG is a lossy type of compression technique, and PNG is a lossless type of PNG technique. Sorry, compression technique. Right. So as you mentioned, because JPEG uses DCT transforms, the edges aren't detected particularly well, and your edges data is lost, as seen in here. Right. So in PNG, there is no such issue because it's a lossless type of formatting, compression technique. So here, since there's no loss of data, the edge remains as it is. So, JPEG is very useful to reduce data size in photos. However, for PNG, it's better for graphics, it's better to use PNG, and PNG is also better for text because in text you can't have afford to lose data. So, if you lose data in characters, for example, then you might lose the information regarding what type of character it is, making your compression redundant. So, on comparison, JPEG is better for photos. Meanwhile, for graphics and text, it's more recommended to use PNG format. So now coming to PDF files. So PDF files have been a huge breakthrough in the form of online data that is received. Nowadays, PDFs are there everywhere, all the way from school up until college to offices. Everywhere you use PDFs. PDFs are used to convey data for many things such as academic journals, your books, research papers, and any official document that is sent, or even, for example, my answers papers, which I have to scan and upload. So PDFs are used worldwide. And so, what is a PDF? A PDF is a portable document format, and a PDF is not as simple as an image or a paragraph. PDF consists of all such data, such as text, images, different types of fonts, right? So, a heading could have a different font size, a bigger font size as compared to paragraphs. It can have the bold font on it and a comparatively different font as compared to the paragraph too. Like, for example, it could be in a different Times New Roman format, and while your paragraph can be in Acacia format. So here we have a small PDF contain a block diagram containing how PDFs work. So each PDF has multiple pages, and each page is documented separately. So each page will consist of various content items such as images, text, paragraphs, and tables. So all these need to be quantized and encoded properly so that when we bring back our our PDF from memory, it should represent the same format as it was built upon. So how does a PDF actually do that? And while ensuring it's doing it in a concise format by storing as less data as possible. So PDF page content is actually divided into continuous streams called marked content sequences. So each marked content sequence consists of various identifiers which help it to decode it in a certain way, right? So in each marked content sequence, you have a different way of encoding or grouping a particular set of images. So some MCS that are there are such as header, your body, and then your content reversed file, and your footer. So each of these has different groups of identification and is responsible for drawing fragments of the page content. Like for example, the body might contain of paragraphs, a continuous stream of text. So it is stored accordingly, right? So how does going more in detail into how PDF compression works? So image compression is the same as we had discussed before. It uses JPEG or JPEG 2000 and the earlier versions for photos. In case you have diagrams and graphics, you cannot afford to lose data, so you go for lossless type of compression techniques. The one used in PDFs is usually flat or zip compression. Right? Similarly, you have a huge amount of text and different types of font compressions. So these are also stored using flat or zip compression techniques. Now coming to object stream compression. So you have like a paragraph, which is a lot of small objects compressed in one stream, or a continuous group of images, all all s- a big image made up of many small images of small objects, right? Such as block diagrams, for example. Block diagrams have a, it is a bigger part of an image, but it is consisting of very small sub-blocks like rectangular blocks attached through arrows, right? And you have cross-reference stream compression. So this actually maps all these objects into its main MCS. So all these small objects, suppose relating to headings, might come under the header MCS, or the ones related to signatures would come under the footer MCS. The page numbers, and then the paragraphs or your figures might come into the body, etc. So these cross-reference stream map it into the MCS or the internal structure of the objects. And then you have other optimizations, like you may have redundant data, such as some random gibberish of text, or you have a repeated amount of data that. Finally, coming to applications and case studies. So nowadays, everything has a software copy, and each software copy is stored in data. And huge corporations require a huge amount of data because almost all information nowadays is stored in software. So there has been a huge market for data centers. It's a very big market, almost $1 trillion, and a lot of the major players are trying for it, such as Meta and Google. Recently, Google and Adani had a deal to set up a data center in India. So such cloud storage systems require to compress these PDFs to save space. So now, with initially we started with traditional compression techniques, as we discussed JPEG techniques. Soon they have even started using DL techniques, and the advantage of DL based compression techniques is that it's a mathematical equation that gives you your compression. So such methods are very useful as it gives you the answer almost instantaneously. And finally, coming to AI-based tools. So what is different in these AI tools is that it adapts your compression based on the content of the document. For example, if it might be a graphics document, it chooses to use PNG, whereas for photos, it'll be better to use JPEG compression, like we discussed before. So the AI tool on its own decides to choose which particular compression technique to apply. Coming finally to conclude and discuss future scope, think image compression improves efficiency and accessibility. Now you're able to record videos and store it in lesser or comparatively lesser data as needed before, as compared to how much you would need before. And PDF compression integrates multiple compression layers, and it's extremely beneficial in today's day and world. So finally, the future scope for this would be to use AI or LLM models, which decide which compression technique to use and to actually divide a document into different sections and to apply particular compression techniques suitable for each section, thereby increasing the efficiency and the speed and the data stored. The challenge here would be to identify how to first thing segregate your data and then how to identify which compression technique to use for which one, right? And then each data once compressed can also be encoded differently. So you can use some stuff like Hoffman coding, concepts like Hoffman coding, which would be way much better to store the data efficiently, and it can help reduce the amount of hardware needed, or sorry, the amount of memory needed for storing this. So, yeah, thank you for attending and watching this video. Bye.